Good morning and welcome to Chapter 2 exercises. So Hershey the cat has decided to grace us with her presence again. I think she heard another cat out there in the yard, so we'll see what happens. Hershey, good kitty. Okay, so Chapter 2 you can see deals with the atomic and molecular structure of matter. The chapter begins with a discussion of hypotheses, theories, and laws. It then goes into the atomic theory and evidence for the existence of atoms. It discusses crystal structures of materials, of solid materials, and then it goes into certain things about the phases of matter, like vapor pressure. So let's check out the exercises. So you can see I have my notes ready. And this video will need to be recorded in several chunks. I haven't worked through all these exercises yet. So the first exercise deals with hypothesis, theory, law, and fact. The second one asks for some evidence of the atomic nature of matter. And then numbers 3 through 7 deal with the crystal structure of solids. And then, or 3 through 6, and then 7, 8, and 9 deal with vaporization and vapor pressure. And then 10 is a little bit different. It asks about models of carbon dioxide. So let's check it out. Oops. There we go. Okay. So exercise 1 was discussed, near the end of chapter 1, actually, pages 13, 14, maybe 15, and then also at the beginning of chapter 2. And maybe to answer this one, we'll use more of the material from chapter 2, but chapter 1 does discuss some of these concepts as well, especially law. Okay, so let's read through this. What are the differences between a hypothesis, a theory, a law, and a fact? And then classify the following statements as hypotheses, theories, laws, or facts. And it gives you several statements, 5 of them. So we'll look at these statements one at a time. But first, let's define these 4 terms. Hypothesis. The text pretty much defines a hypothesis as an idea that explains or correlates a number of experimentally observed facts. So if you observe something by experiment, it's obviously happening. Then if you're able to explain what's going on behind that fact, that's a hypothesis. Okay, a hypothesis is an attempt to explain an experimentally observed fact. Now, a hypothesis can be elevated to a theory as follows. A hypothesis that undergoes further testing and experimental checking of deductions that may be made from it. If it continues to agree with the results of experiment, the hypothesis is then called a theory. So if you have a hypothesis that explains a certain number of experimentally observed facts, if you further test that hypothesis, and also suppose the hypothesis, you have deduced certain things from it, if you've tested those deductions, and if the hypothesis continues to remain valid, so it's been actually tested now a number of ways, then you can call the hypothesis a theory. So you know that the hypothesis was a good explanation. Okay, it's been tested many different ways, and you can call it a theory now. Okay, now perhaps we'll mention fact first. A fact is something known to be true by experiment or observation. So it's something you actually observe, and it's obviously true because you observed it with your eyes or through some other experimental methods. So that's an observational fact. What a law is it's a summarizing statement about a number of experimentally observed facts. So if you observe a number of things, you have a whole collection of facts, then you can summarize that whole collection with some sort of law, a summarizing statement. Now, in my classes, I like to sort of differentiate these two terms with those two terms. These two terms sort of explain why something happens. And those two terms, tell you what happens, right? Okay. So let's go ahead and look at these statements. Okay, and you can see I've classified them, color-coded them. The hypothesis is yellow, the theory is blue, law is pink, and fact is green. So the statements have been classified. Okay, so the first statement says, the interior of the moon consists of granite and similar silicate rocks. Now, I had to kind of think about this one. Have scientists observed the interior of the moon? Have they brought up any drills to drill out the interior and look at samples and then, see it with their own eyes and with their own machinery? No, they probably haven't done that yet. We haven't been to the moon in 50 years? I think we're going in a couple years or something, or next year. But the interior of the moon hasn't directly been observed yet, and so this is kind of a guess. Okay, we think the interior of the moon might consist of granite and similar silicate rocks, and perhaps the rocks on the surface. If you look at the rocks on the surface, that might give you information as what might be occurring inside the moon. Okay, so I would think that this is classified as a hypothesis. It's not yet checked, but it may explain the material found on the moon's surface. Okay? It might explain what you see on the moon's surface. So, if this is true, if this hypothesis is true, then that would make sense, that the stuff on the surface is also granite and similar silicate rocks. Okay, now the second one, hydrogen, nitrogen, oxygen, and neon are all gases under ordinary conditions. All right, I would say that this is a fact that's already known to be true. We have observed hydrogen, nitrogen, oxygen, and neon under ordinary conditions many, many, many times, and we know that they're all gases. Okay, so that's an experimentally observed fact. Okay, it's obviously true. The next one. A force acting on a body with mass m causes it to be accelerated by the amount F times m to the negative 1, or F over m. Okay? Now, for you physics students, you probably know this to be Newton's second law of motion. Okay, so this is Newton's second law. If Newton called it a law, we're going to call it a law. So this is observed over and over again. Okay, when you apply a force on a certain object, it accelerates that object. Okay, we have seen this over and over again. When you push something, you accelerate that object, and this has been summarized by the following statement. All of these observations have been summarized by Newton's second law. It says that if you push an object with a certain force and that object has a certain mass, then it is accelerated by this amount, F over m. Right? So Newton's second law is, of course, F equals ma. And so if you solve for the a, it would be F over m. D, the properties of gases can be explained by considering the motion of the molecules composing them. So that's the key word here, explaining something. Now, this is explaining a lot. The properties of gases, that's a whole lot to explain, okay? And so it's probably not a single hypothesis. A single hypothesis usually explains a certain observation or a small set of observations to, explain a lot more. That's going to be a theory, okay? This has been well tested, okay? The properties of gases have been tested over and over in the lab, and they are explained by considering the motion of the molecules composing them. There is the kinetic theory of gases, okay? By assuming that gases are made of small particles, that explains all of their properties, pressure, Brownian motion, all kinds of things. And we'll actually discuss some of them in the next problem. Okay, so I would say that's a theory. It's a well-tested hypothesis. The last statement, all crystals contain atoms or molecules arranged in a regular way. Now, when I first looked at this statement, I thought it would probably be a law, because crystals have been directly observed many times, and all kinds of different crystals have been observed, and every single one of them we see, with the aid of special instruments, the atoms are all lined up. So I would think that this would be a summarizing statement to all of those experimental observations. But then I searched the text, and I noticed that Pauling discussed theory, the word theory, as being used in two different ways. Okay, the first way that a theory is used is it's a hypothesis that's undergone further testing. That's how we defined it. A hypothesis that's undergone further testing and experimental checking of deductions that may be made from it. If it continues to agree with the results of the experiment, then the hypothesis is elevated to the status of theory. But the text, here I'll zoom in a little bit. You see, I thought it was something observed again and again by X-ray crystallography, atomic force microscopy, many different experimental methods you can directly observe crystals. Okay, we'll talk about that in the next problem a little bit. Now, the text does mention on page 17 the atomic theory of crystals. Okay? Now, this is the theory that in crystals the atoms are arranged in a regular order. And theory in this sense also means a systematic body of knowledge compounded of facts, laws, theories, and deductive arguments, etc. So theory can also be used in a more general sense, that it's all of those things kind of put together. You have the theory of crystals, which contains a large body of knowledge. So not only explanations behind the observations, but also certain facts and laws and other smaller theories as well. So the atomic theory of crystals contains all of those things. So here I've outlined it in blue. So that's a different sense of the word theory, and I think that's what Pauling was kind of thinking about when he put this statement in here. He's talking about the theory, the atomic theory of crystals, and that way the theory is used in a larger sense. Some of the evidence for the atomic nature of matter. Now the textbook provides a few pieces of key evidence in chapter 2. It mentions the law of constant composition, and also a couple of more direct pieces of evidence, which include electron microscopy and X-ray crystallography. I'd like to add a few others as well, and we'll split them into pieces of indirect evidence and more direct evidence. The direct evidence are methods that allow us to really see atoms in a way. So the indirect evidence, we've already mentioned the law of constant composition. Now this was known before the first atomic theory of Dalton. The law of constant composition says that different samples of a substance, of a compound really, contain the same proportions of its elementary constituents. So compounds always have the same proportions of elements. For example, water always contains 89% oxygen and 11% hydrogen by mass. Now, this law for compounds is explained well by the atomic theory. For instance, the way we can explain this is by looking at the smallest particle of water, which is a single molecule. Now, a single molecule contains one oxygen atom, which weighs 16 atomic mass units, and two hydrogen atoms, each weighing 1 atomic mass unit. So if you look at the smallest unit of water, these are the constituents. Now, if you calculate the proportion of oxygen, 16 atomic mass units, you divide it by the total mass, which is 18, then that is 89% oxygen. So this molecule is 89% oxygen, and the rest of the percentage is hydrogen. And if you scale that up to 2 molecules, you still have the same proportions. In any amount of water, you still have the same proportions. So it just makes sense. The atomic theory does explain this law. They mesh together. Another piece of evidence is the well-known behavior of gases. So gases, it's been known that when you squeeze a gas into a smaller volume, it exerts a larger pressure. Well, this is explained by the atomic theory. For instance, suppose you have a gas trapped inside of a container, a piston, where you can squeeze it down to smaller volumes. Okay? These atoms are constantly flying around in the gas phase, and the pressure is due to collisions with the walls and with the pistons. Okay, now at a larger volume, the gas exerts less pressure because there are less frequent collisions with the walls of the container. So the collisions are less frequent, it's a lower pressure. Now, it is harder to squeeze the gas into a smaller volume. You have to add extra weight to the top of the piston, and when you do that, the collisions are more frequent, and therefore a higher pressure. And you can actually feel this. If you try and compress a gas, it gets harder and harder to compress it, and you can imagine that's because of the atoms in there that are colliding more and more frequently. Okay, and if you wanted to squeeze it down to a smaller volume, you would have to add more force, more weight. Okay? There are lots of behaviors of gases that can be explained by the atomic theory. One more is that when a gas is at a higher temperature, it diffuses more quickly. Imagine you're inside of a cold room and you're standing in one corner, and someone at the other corner releases some volatile gas, like maybe a perfume. Well, it will take a while for these gas molecules to work their way towards your end of the room. You know, they don't travel in a straight line, they kind of collide with different molecules along the way, but it takes a certain amount of time for you to smell that perfume. Now, if you were to crank up the temperature in the room, the gas molecules would be moving more quickly, right? They have more kinetic energy, and you're going to smell the volatile substance more quickly. So again, it just makes sense that things are made of particles, and at a hotter temperature, the particles move faster. Okay? So these two, again, mesh with these two well-known behaviors of gases are explained by the atomic theory. Now, a third piece of indirect evidence is Brownian motion. Brownian motion. Now, Brownian motion, we'll show a video here in a second. It's basically the erratic random motion of microscopic particles in a fluid, and they are as a result of the continuous bombardment of molecules of the surrounding medium. It kind of is sort of like when molecules work their way across the room, they don't move in a straight line. Even though they move very quickly, they collide with many other molecules along the way. So it takes you, a minute or so to smell the perfume, and that's because the perfume molecules are colliding along the way. Okay, but these perfume molecules are actually invisible and you can't see them. However, when you're dealing with larger molecules suspended in a fluid, you actually can see them moving, and you see them moving in some erratic, random type of motion. It's very weird. So let's check out this video that I have ready for you. It's on YouTube. I found a cool video.
They jittered and moved. Brownian motion. Here you can see tiny plastic beads in water, seen through a microscope. The beads are only 1/1000th of a millimetre across. In 1827, scientist Robert Brown was studying pollen grains in water. He noticed that the grains of pollen were constantly moving. They jittered and moved about randomly. He suggested that the pollen grains are moving because they were alive. He repeated the experiment with soot grains which he knew were not alive, but he saw that they moved in the same way. He could not explain what he had seen. These are soot particles floating in air. In 1905, Albert Einstein proved that the movement was caused by tiny, invisible, fast-moving particles hitting the pollen grains.
Okay, so this part right here, when you see one of those random, when you see that motion, that random motion of a microscopic particle, here I'll show it to you again.
A millimetre across.
You see him kind of bouncing
In
around.
1827, scientists.
Well, the reason that's happening is because they're constantly being bombarded by the surrounding water molecules. Okay, the surrounding water molecules are hitting the microscopic particles. Sometimes there are more water molecules hitting this side, which pushes the microscopic particle one direction, and then other times there are more collisions hitting this way, which pushes water that way. And it looks, since we're not able to see the water molecules, it looks like the Brownian motion is just some random motion. But Albert Einstein showed that, it makes sense that the microscopic particles are surrounded by smaller particles, atoms, or molecules that we just can't see. Okay? So it makes sense. Now, okay. So again, Brownian motion is explained very well by the atomic theory. Now, the next three pieces of evidence are more direct. Okay? Electron microscopy, X-ray crystallography, and atomic force microscopy. Now, electron microscopy is a special type of microscope that uses a beam of electrons to create an image. You can imagine some surface that you're trying to take an image of. Well, optical microscopes only go down to about a micrometer. If you want to see closer than that, then you need a special type of microscope, and an electron microscope can see maybe 1,000 times smaller, even more so. And the way it works is you shoot a beam of electrons, a focused beam of electrons, onto the surface, and the electrons are deflected by the individual atoms on the surface. And when you move this beam around, that changes the path of deflection. And so you create a sort of image of the surface. And these images are really amazing looking sometimes. So I'd like to show you some images of that use electron microscopy that are so much more zoomed in than optical microscopes. So here's a an image of an ant that was taken using an electron microscope, and the detail is just amazing. Okay, but it gets better than that. You can zoom in on the eye of an ant, and look at how close we're able to see. Okay, that's an ant's eye, but you can even go closer than that. You can see individual cells. So these are red blood cells, and also they're in contact with lung cells, I believe. So you're getting down to the cellular level, but you can even go beyond. We can start to see individual atoms, in fact. So this next image is that of graphite. Okay, and it's not the black particles, it's actually the red particles are the carbon atoms. Okay, you can actually see individual atoms using an electron microscope. So pretty cool. So we're actually able to see atoms now. Okay, very direct evidence. Okay, so the next piece of direct evidence is that of X-ray crystallography. And instead of using a beam of electrons, it actually uses a beam of X-rays. Okay, and those X-rays are deflected and hit some detector. And X-ray crystallography doesn't really give you an image. It kind of tells you where the atoms are, though, and you're able to determine atomic positions. And so you basically get, the computer that the detector computer analyzes the data, and it tells you where the list of positions are. And you can use software to generate an image. So you basically determine the X, Y, Z coordinates of where the atoms are using this method right here, and it's up to you to create your own type of image, kind of an artist's rendition. And there's all kinds of software out there, and I'll show you some images using X-ray crystallography. So here is a piece of DNA. Now, the positions of these atoms are accurate, but this is not an actual visual image like scanning electron microscopy was. Okay, this is what a software draws, and this is one rendition, but we could draw a piece of DNA, you know, as a ribbon. You know, there's many different ways to draw the actual molecule. Another, you know, picture that we can do is that of a protein. So here is a protein, and you see these ribbons right here are actually, we're not drawing the atoms, we're just kind of connecting the atoms with a ribbon, but this ribbon is, you know, experimentally accurate. There are atoms along this ribbon right here, but instead of drawing the actual balls, we're just, you know, sort of making a fluid ribbon. Okay, and here's a couple of other molecules that are attached to the protein where the atoms are maybe drawn a little bit more clearly. Okay, so anyway, it takes an artist's rendition or a software rendition to, you know, create the image. But still, you're getting, you know, you're identifying where the atoms are. Okay, direct evidence. So another piece of direct evidence is atomic force microscopy. Now, atomic force microscopy is sort of like a microscope that feels its way around the surface, and you can feel the individual atoms on the surface. What you have is an atomic pointed needle that feels its way along the surface, and I'll show you what that machine sort of looks like. So you see you have a needle, and at the end of the needle you have a carbon monoxide molecule, so an individual atom. Okay, and this needle sort of scans its way along the surface, and it can feel, you know, the existence of atoms. Okay, and the needle sort of moves up and down, and then that sends information to the computer, which generates an image of the surface. Okay, so atomic force microscopy is a really cool and powerful method to detect atoms. And here is you know, some images obtained of this molecule. This is C26H14. Okay, you can see here is an atomic force an atomic force image of this molecule versus an scanning electron microscopy image of the same molecule. So you get a little bit more detail with atomic force versus electron microscopy. You can still detect the atoms here, but it's kind of hard to see. Okay, a little bit more detail. And when this molecule undergoes a transformation, it forms this one. This is the atomic force image of it versus the electron microscopy image. So very powerful techniques here to see individual atoms. There are lots of other experimental methods, NMR, IR, UV-Vis, spectroscopy methods. Okay, there's probably a lot more. Anyway, so lots of evidence out there for the existence of atoms, both indirect and direct.